2 weeks ago, 3I Atlas soared past Mars at a staggering 29 million kilometers with surgical precision. For months, it's been unleashing a torrent 144 metric tons of water per hour laced with nickel cyanide and ionized plasma. This isn't random cosmic debris. It's the precise molecular recipe for metalloproteins, where biology fuses with technology. In 2 years, Elon's robots will touch down on Mars, constructing infrastructure and birthing new machines. Mars just received a package from another star system. The chemistry flawless. The timing impossibly perfect. What if this was always the plan? This is a thought experiment grounded in real science, but the facts are undeniable. If you're as gripped as we are, smash that like button and subscribe. Drop a comment below. Tell us where you're tuning in, from what time it is there, and if you think we're witnessing the dawn of a new life form. Want to help our community grow? Share this on X, Facebook, Reddit, or Messenger. Thank you for always having our back, cosmic gardeners. What if 3I Atlas is seeding Mars? On October 3, 2025, something extraordinary unfolded in the void between worlds. An object from another star system hurtling at over 200,000 km/h grazed past Mars, at a distance most would call astronomical, 29 million kilometers, roughly 75 times the Earth-Moon gap. In the vastness of space, that's a near miss. But this wasn't just a fleeting visitor. This was a delivery. A bold ex-user laid it bare. 3I Atlas is a seed, not a metaphor, not a poetic flourish, but a literal catalyst for metal-based organic life on Mars, potentially sparking the next generation of intelligent beings in our solar system. Before you brush this off as sci-fi fantasy, let's unpack what we know from observatories, space telescopes, and peer-reviewed papers published in the last 2 weeks. Since we first spotted 3I Atlas in July, it's been gushing water, not a trickle, but a deluge. The Neil Gerald Swift Observatory clocked its outflow at 40 km per second. That's 88 pounds every second. Picture a fire hose cranked to full blast running non-stop since early summer. The numbers are mind-boggling: 144 metric tons per hour, 456 metric tons per day, enough to fill an Olympic swimming pool daily for months. Water alone isn't the story. Water's everywhere, frozen in comets, buried in lunar soil, even drifting in the clouds of gas giants. What makes 3I Atlas electrifying is its cargo. In late August, the KEK Observatory in Hawaii trained its instruments on this cosmic wanderer, hunting for clues beyond the ordinary. What they found could rewrite our understanding of life itself. The chemicals you'd expect from a comet nearing the sun, not here. What 3I Atlas is releasing defies every model of natural cometary behavior. The KEK Observatory in Hawaii detected something astonishing: strong, concentrated nickel emissions without a trace of iron. Pause and consider that. In nature, nickel and iron are cosmic twins forged in the hearts of dying stars, expelled in supernovae, and traveling together in every comet, asteroid, or space rock we've ever studied. The ratio might shift, but both are always present. Always. Until 3I Atlas. This object is ejecting nickel at 5 GLs, pure, unadulterated nickel with zero iron. A research team's October paper flagged something unsettling. This nickel without iron signature isn't unheard of, but it's not natural. It mirrors the output of industrial nickel refinement facilities on Earth, specifically the carbonyl process. In that process, nickel ore is exposed to carbon monoxide under precise conditions, forming nickel tetracarbonyl, a compound that breaks down to yield pure nickel. It's a technique we've used since the early 20th century, and now it's happening on an interstellar comet. Or as Avi Loeb hinted in his Medium post, perhaps not naturally at all. But nickel is only half the story. The other half, cyanide, specifically hydrogen cyanide HCN, pouring from 3I Atlas's coma in ever-growing quantities as it nears the Sun. The Very Large Telescope in Chile tracked this in real time through August and September, measuring 20 GeV by late August. By mid-September, the James Clerk Maxwell Telescope recorded 1.5 x 10 25 molecules per second. A week later, that number had tripled. The production rate follows a power law distance from the Sun to the power of 9.4. This isn't a gradual rise. It's an exponential surge. Here's where the chemistry gets eerily perfect. Nickel cyanide and water, the exact ingredients for metalloprotein's molecules that blur the line between biology and technology. The implications are staggering. Is 3I Atlas seeding Mars with the building blocks of a new form of life? Drop your thoughts in the comments. Where are you? What time is it? And do you think we're witnessing something cosmic? Share this on X, Facebook, Reddit, or Messenger to spread the word. Thank you, Cosmic Gardeners, for joining this journey. 2 weeks ago, on October 3, 2025, an interstellar marvel named 3I Atlas blazed past Mars at a breathtaking 29 million kilometers a distance that in the cosmic scale of things is a mere whisper, roughly 75 times the gap between Earth and the Moon. This wasn't just a flyby. It was executed with surgical precision, as if choreographed by some unseen intelligence. For months, this enigmatic object has been unleashing a torrent into the void, 144 metric tons of water every hour, laced with nickel cyanide and ionized plasma. This isn't random space debris. It's the precise molecular recipe for metalloproteins, those uncanny hybrids where biology and technology converge. In just 2 years, Elon Musk's robotic pioneers are set to land on the Red Planet, constructing infrastructure and spawning new machines. Coincidence? Or something more? Metalloproteins already embody that fusion of the organic and inorganic, a dance where life hinges on metal cores. Hemoglobin relies on iron to carry oxygen. Chlorophyll depends on magnesium to capture sunlight. Vitamin B12 needs cobalt to function. Strip away the metal, and these proteins collapse lifeless, inert. But what if the metalloproteins taking shape on Mars aren't like ours? What if they're not carbon-based life with metals as supporting players, but metal-based life where nickel forms the core and organic molecules are mere scaffolding? This isn't wild fantasy, it's a logical extension of what we see in nature. Consider iron-sulfur clusters, some of the oldest catalytic structures in biochemistry. Found in bacteria, archaea, and the enzymes that power modern cells. These tiny inorganic machines shuttle electrons, drive reactions, and make life possible. Now imagine scaling that up, swapping iron for nickel, and you've got a blueprint for something entirely new, a life form where metal is the foundation, not the accessory. The data from 3I Atlas spewing nickel cyanide and water points to this possibility, with chemistry too precise to ignore. Then there's the plasma trail. The piece no one's talking about yet, but it could be the key. As 3I Atlas streaks through space at over 200,000 km/h, it's not just scattering chemicals like seeds from a cosmic sour. It's carving an ionized wake, a trail of charged particles shaped by magnetic fields and solar wind. Plasma isn't just gas. It's matter's fourth state, a dynamic soup of ions and free electrons. This plasma carries more than raw materials, it holds information. Not like a radio signal, but in its structure, the patterns of density, the twists of magnetic field lines, the oscillations of electric potential. Plasma has memory. An ex-user pointed out that Mars is receiving this delivery in both physical and informational forms. The physical is clear dust grains, ice particles, water, cyanide, and nickel vapor, all drawn into Mars's gravity, well mingling with the regolith. But the informational part is subtler. plasma structures can persist, propagate, and interact. When solar wind strikes Earth's magnetosphere, it doesn't just deflect it, triggers complex interactions, auroras, and energy transfers. On Mars, with its thin atmosphere and weak magnetic field, this plasma wake could be imprinting patterns, encoding something we don't yet understand. 2 weeks ago, 3I Atlas passed Mars at 29 million kilometers, unloading 104 metric tons of water per hour, laced with nickel and cyanide ingredients for metalloproteins that could redefine life itself. In 2 years, Elon's robots will land building infrastructure and new machines. Is this a cosmic coincidence? Or was it always the plan? The science is real, the question's urgent. If this grips you, smash that like button and subscribe. Tell us in the comments, where are you, what's the time? And do you think we're watching the birth of a new life form? Share this on X, Facebook, Reddit, or Messenger to fuel the conversation. Thank you, Cosmic Gardeners, for joining this journey into the unknown. The plasma trail of 3I Atlas isn't just a cloud of charged particles. It's a cosmic symphony of waves and stabilities patterns rippling through the void. When solar wind collides with Earth's magnetosphere, it creates auroras, energy transfers, and structures that can linger for hours or even days. The plasma wake trailing 3I Atlas could be doing something similar, but on a grander scale. It's not just dumping chemicals. It might be carrying a template for organization, a set of initial conditions that could nudge whatever forms on Mars toward a specific kind of complexity, perhaps a new form of life or something stranger. This plasma, with its density patterns, twisting magnetic fields, and oscillating electric potentials, has memory. It could be encoding instructions we can't yet read. And then there's the timing where coincidence begins to feel like choreography. On October 3, 2025, 3I Atlas made its closest approach to Mars, a mere 29 million kilometers, a cosmic near miss. Fast forward to late 2026 or early 2027, and SpaceX's uncrewed Starship missions are slated to land carrying Tesla's Optimus robots. These humanoid machines designed to walk, lift, and wield tools have a clear mission build. They'll construct solar arrays, habitats, and resource extraction systems, laying the foundation for human colonies. But they won't stop there. According to Elon Musk's public statements, these robots will also build more robots, self-replicating machines that learn and adapt. Now picture this. By the time Optimus units are carving out Martian bases, the materials from 3I Atlas will have been settling on the surface for 2 years. Nickel atoms embedded in dust, cyanide molecules frozen in ice water scattered across craters and canyon floors. The robots won't be searching for these materials. They'll be focused on digging foundations, processing regolith, and analyzing resources. But they'll encounter them. Nickel, cyanide, water, the exact ingredients for metalloproteins, those hybrid molecules, where biology and technology blur. On Earth, metalloproteins are indispensable. Hemoglobin needs iron to transport oxygen, chlorophyll relies on magnesium for photosynthesis, and vitamin B12 hinges on cobalt. Remove the metal and the biology collapses. Remove the biology and the metal is just a lump. They're interdependent. What happens when self-replicating machines meet the chemical building blocks of a different kind of self-replication? Do they compete, cooperate, or merge? On Earth, metalloproteins bridge the organic and inorganic. Could they do the same for silicon-based machines with their circuits, actuators, and learning algorithms? Perhaps the nickel-rich compounds now settling into Martian soil are the catalytic spark these machines need to evolve from programmed tools to something adaptive, something more. An ex-user hinted at this not explicitly, but in the subtext, 3I Atlas isn't just a comet. It's infrastructure preparation, like tilling soil before planting or fertilizing a field before sowing seeds. It's delivering the raw materials for a biological or hybrid process that doesn't yet exist, but could, given the right conditions, like a fleet of intelligent machines capable of manipulating matter at a molecular level and driven to optimize their own designs. This is the seeding hypothesis. 3I Atlas isn't carrying life, but the potential for it. Water, cyanide, and nickel are the ingredients, the starter culture, and Mars, with its thin atmosphere, low gravity, and stable surface, is the petri dish. Let's be clear, this is speculation, but it's grounded in hard data. The nickel without iron, a signature only seen in Earth's industrial processes. The exponential cyanide production, measured at 1.5 x 1025 molecules per second by mid-September, tripling in a week. The water output, 144 metric tons per hour, defying conventional cometary models. The trajectory bringing 3I Atlas within spitting distance of Mars, just as humanity gears up to send robots there. Any one of these could be a fluke, a natural quirk. Together, they form a pattern. In science, patterns are the signal in the noise, the structure in the chaos, the hint of something deeper. The probability of this alignment feels less like a coin flip and more like the kind of odds that make astronomers triple-check their calculations. The close approach of 3I Atlas coincidence or calculation, it's a question that demands exploration. So where are you right now? What's the time there? Do you think we're witnessing the birth of something new on Mars? Drop your thoughts in the comments and share this on X, Facebook, Reddit, or Messenger to keep the cosmic conversation alive. Thank you, Cosmic Gardeners, for joining us on this mind-bending journey into the unknown, the kind that surfaced in the orbital mechanics of 3I Atlas as it hurtled toward Mars. 29 million kilometers sounds vast. It is vast. Yet in the grand tapestry of interstellar space where an object might traverse light-years of void for billions of years, 29 million kilometers is a mere flicker, a hair's breadth, a whisper. The precision required for such a close approach, considering 3I Atlas's origins and its blistering speed, is nothing short of staggering. A vibe calculated the minimum orbit intersection distance, or MOID, between the comet's trajectory and Mars's orbital path, 2.7 million kilometers. That's the nearest their paths come to kissing in the vastness of three-dimensional space, not where the objects themselves were, but where their orbits align. Here's why that matters. 3I Atlas follows a hyperbolic trajectory not bound to the Sun's orbit, but slingshotting past it, accelerating as it departs forever. Its path is sculpted by its distant origins, its entry speed into our solar system, and the gravitational nudges from the Sun and planets it encountered. An interstellar object like this can't be steered. Natural objects lack engines. They don't adjust course. They obey the unyielding laws of physics, following ballistic arcs set by their initial conditions. So when an object on such a trajectory passes within 30 million kilometers of a planet, you're forced to wonder how. The answer, more often than not, is sheer chance. But 3I Atlas didn't just graze Mars. Its trajectory aligned eerily with the ecliptic plane, the flat disk where all planets orbit. Most interstellar visitors plunge through our solar system at sharp angles, diving from above or below, as space is three-dimensional with no favored direction. The odds of an object arriving on a path so neatly aligned with the planetary plane by pure chance, roughly 1 in 500, a 2% probability, already unsettling, but it deepens. The direction of arrival matters too. 3I Atlas originated from the constellation Sagittarius, pointing toward the galactic center, the dense disk of the Milky Way, where ancient stars and their primordial planetary systems reside. This isn't idle trivia. This trajectory suggests 3I Atlas hails from a galactic region where stellar populations differ starkly from our own lower metallicity distinct chemical compositions, and critically, potentially far older systems. Systems born when the universe was young, its elemental mix fundamentally different. If you were to design a probe to explore or influence nascent planetary systems, you'd launch it from an ancient, mature system, one that had already mastered the progression from chemistry to biology to technology. Lowe's paper, co-authored with Adam Hibbett and Adam Craw, laid out the math. If 3I Atlas had executed a velocity shift of 10 to 15 km/s sometime in September, its close approach would collapse to zero, a direct intercept, not a mere flyby. A collision, or if the object were advanced enough, an orbital insertion. 15 kilometers per second sounds immense. It is. For a natural comet reliant on gas and ice sublimation, such a velocity change is impossible. The Very Large Telescope measured the outgassing speed of particles from 3I Atlas at 4 km/s, the upper limit for what sublimating ice can achieve without external forces. To redirect toward Mars would require 37 times the thrust natural outgassing could provide. 37 times. But here's the kicker: engineering changes the game. If you have any form of controlled propulsion, 15 km isn't insurmountable. It's less than Earth's escape velocity, a fraction of the delta-V budget for a Mars mission. For something with an engine, even a modest one, it's within reach. The fact that we didn't detect such a maneuver doesn't mean it didn't happen. It means we weren't looking, or it was subtle, masked within the chaotic plume of water and carbon dioxide enveloping the nucleus. A brief burn, a course correction, veiled by natural outgassing. The timing only heightens the strangeness. 3I Atlas was spotted on July 1st. By late July enough, observatories had tracked it to confirm its hyperbolic orbit and predict its close approach to Mars in early October. A 3-month window. 3 months in which anyone with the tools to analyze orbital data would see this object barreling toward the red planet. And in that same window, its outgassing activity surged dramatically. The water production doubled. The cyanide output tripled. Nickel emissions surged exponentially, as if 3I Atlas were awakening, priming itself, unloading its cargo in the final stretch toward Mars. Now picture the geometry from Mars's vantage point. On October 3rd, Mars occupied a precise spot in its orbit. 3I Atlas, in turn, swept past at a specific point in its trajectory. For those 2 points to align, given the 7-month journey from Jupiter's orbit, where the object first became visible, the launch timing had to be impossibly exact. Not just skimming the ecliptic plane, not just passing near Mars, but passing near Mars when Mars was there. Planets don't loiter. They move. Mars takes 687 days to complete one orbit. Had 3I Atlas arrived a month earlier or later, the close approach distance would have been wildly different. Mars would have been elsewhere. The encounter would have fizzled. This is where coincidence starts to feel uneasy. We're not talking about a single stroke of luck. We're talking about a chain of pinpoint events, an arrival angle aligned with the planetary plane, an origin from an ancient, chemically distinct galactic region, a trajectory grazing Mars's orbit, and timing that places Mars in exactly the right spot. All this just 2 years before humanity plans to land robots on the red planet. You can chalk it up to chance. The universe is vast, and strange things happen. But when coincidences pile this high, you're forced to entertain alternatives. Lowe's hypothesis, proposed cautiously with caveats, is that 3I Atlas might not be entirely natural, a probe, a vessel, or a delivery system with some degree of guidance. He rated it a 4 on his scale for anomalous objects, not proof, not even strong evidence, but peculiar enough to demand serious scrutiny. Dismissing it outright would be unscientific. The Mars flyby is the crux of this anomaly. To deliver something to Mars, to hit the right time and place, you'd need to aim. You'd need to calculate. You'd need to engineer the trajectory. There's more. The MOED, the 2.7 million kilometer closest approach between orbits, represents either a vulnerability or an opportunity depending on your lens. If 3I Atlas carried smaller objects, sub-probes, fragments designed to detach, they wouldn't need much thrust to reach Mars from that distance. Low modeled this explicitly launch a small precursor probe from 3I Atlas in August or early September, give it a modest velocity nudge, and by October 3rd, it hits Mars. The main body sails past at a safe distance, but the payload delivers. We have no evidence this happened, no observed separation events, no detected fragments. But absence of evidence isn't evidence of absence, especially when searching for something small and dark against the cosmic backdrop. The high-rise camera on the Mars Reconnaissance Orbiter was trained on 3I Atlas during the flyby. It captured images. Those images remain unreleased. NASA, ESA, and the teams operating Mars orbiters have stayed silent about what they saw. Perhaps it was just a fuzzy blob, an unremarkable comet at long range. Or perhaps not. Or perhaps they saw something else, something demanding deeper analysis, something requiring careful framing before public release. The plasma trail adds a fascinating twist to the delivery mechanism. Ionized particles don't travel in straight lines. They spiral, drift, and scatter, guided by magnetic field lines and the solar wind. Mars lacks a global magnetic field, its core having cooled billions of years ago, but it retains patches of crustal magnetization, especially in the southern highlands. It also has an induced magnetosphere, a bubble shaped by the solar wind's interaction with its upper atmosphere. These structures could channel plasma steering charged particles from 3I Atlas's wake toward specific Martian regions. Not a random scatter, but a targeted deposition. Think of electrons in a cathode ray tube. They're not sprayed haphazardly, but focused by magnetic fields to paint precise patterns. On a planetary scale, the same principle applies. If 3I Atlas's plasma trail carried a structured charge, Mars's magnetosphere could act like a lens, funneling nickel ions and organic molecules to the surface in patterns dictated by its magnetic topology. This isn't science fiction, it's plasma physics. We see it in Earth's auroras, where charged particles follow field lines to ignite the polar skies. On Mars, with its thin atmosphere, those particles could reach the ground. Here's the kicker. The southern highlands, where Mars's crustal magnetic fields are strongest, host its oldest terrain, Noachian rocks, 4 billion years old. A stable ancient surface where chemistry could unfold slowly, where minerals could accumulate, where a seeded payload would find an ideal landing zone. 3I Atlas's close approach traced a path over the southern hemisphere perfectly aligned for plasma deposition in those regions. Chance or targeting? This raises a deeper question buried in the math and orbital mechanics. What does intentionality look like from the outside? When you observe a highly improbable but not impossible event, how do you distinguish luck from design? You search for patterns, for deviations from what chance predicts. 3I Atlas brims with such deviations chemistry that shouldn't exist, a trajectory threading multiple needles, timing that aligns with human exploration plans. Each anomaly might be explainable alone. Together, they're harder to dismiss. And the Mars Reconnaissance Orbiter wasn't the only asset watching. ESA's Mars Express and ExoMars Trace Gas Orbiter also turned their instruments toward 3I Atlas. Spectrographs dissected the comet's light, cameras captured its morphology, and particle detectors scanned for anything reaching Mars's vicinity. The data is still being processed, and what's public remains sparse. ExoMars TGO caught a faint white dot in its images. Mars Express gathered spectroscopic data on the coma, but the full analysis detailing what filled the three-dimensional space between comet and planet hasn't surfaced. Processing takes time. Verification takes time. Deciding how to frame potentially groundbreaking or utterly mundane findings takes time. For now, we're left with the numbers: a 2.7 million kilometer MOID, a 29 million kilometer close approach, a 2% chance of ecliptic alignment, a surge in outgassing activity in the 3 months before the encounter, and a delivery window hitting Mars precisely 2 years before human robots begin building infrastructure. Call it coincidence. Lean on the anthropic principle: we notice patterns because we're here to see them. But the precision is undeniable. In nature, such precision signals either staggering luck or an underlying mechanism, some force process, or intent shaping outcomes beyond random chance. The question isn't whether 3I Atlas hit an unlikely target. It's whether that target was chosen. Then there's the industrial signature nickel without iron. Every good detective story has a clue that doesn't fit: a fingerprint out of place, a chemical trace, tying disparate events. For 3I Atlas, that clue emerged on August 24th, when the Keck Observatory in Hawaii aimed its cosmic web imager at the comet and shattered 70 years of cometary science. Pure nickel emission. No iron. To grasp why this matters, consider stellar nucleosynthesis, the forge of elements inside massive stars. Fusion builds heavier elements, step by step: hydrogen to helium-helium, to carbon-carbon to oxygen, climbing the periodic table until iron. Iron is the endgame. Fusing it consumes more energy than it yields, so stars don't bother. When a massive star exhausts its fuel, its core collapses, triggering a supernova. In that cataclysm, a flood of neutrons and energy births heavier elements: nickel, copper, zinc, gold, in mere seconds, blasted into space. Here's the crux: nickel and iron are forged together. They're not just periodic table neighbors. They're siblings of the same supernova process. Iron 56 and nickel 58, both stable, both produced in similar abundances. When a star dies, its debris, dust, asteroids, comets, planets, carries this mix. Every sample we've studied, from meteorites to moon rocks to Martian soil, shows nickel and iron together. The ratio varies, but both are always present. Always. Until 3I Atlas. Keck's data revealed strong, unmistakable nickel emission lines, fluorescing in sunlight, concentrated near the nucleus, and extending 600 kilometers outward. The team searched for iron at its characteristic wavelengths. Nothing. The instrument's sensitivity would have detected iron at just 10% of nickel's abundance. It didn't. The upper limit for iron was effectively 0. In hundreds of comets studied with spectroscopy, this has never happened. Not once. Not in 2I Borisov, the prior interstellar visitor, which showed nickel and iron in the expected ratios. Not in Hale-Bopp Hyakutake, or any great comet gracing our skies every few decades. 3I Atlas stands alone. In a population of hundreds, standing alone isn't neutral. It's a glaring flag demanding explanation. The Keck team proposed a mechanism: the carbonyl process, specifically nickel tetracarbonyl formation near the nucleus. Here's how it works on Earth. Take nickel, often impure and mixed with other elements, and expose it to carbon monoxide gas at modest temperatures, around 50 degrees Celsius. The nickel reacts with CO to form nickel tetracarbonyl, a volatile compound that evaporates. Collect the vapor, heat it, and the compound decomposes, depositing pure nickel. Discovered in 1890 by Ludwig Mond, this process, known as the Mond process, revolutionized metallurgy and remains in use today. It's industrial chemistry, human ingenuity, and now apparently cometary chemistry. The Keck team suggested that carbon monoxide in 3I Atlas's coma combined with nickel atoms from the nucleus, forming nickel tetracarbonyl in situ. This compound, unstable in sunlight, would break down quickly, releasing nickel atoms. Iron, however, doesn't form a stable carbonyl under the same conditions. Iron pentacarbonyl exists, but requires different temperatures and pressures. So if the carbonyl process is at play, it could preferentially release nickel, leaving iron behind. That's the natural explanation, the one avoiding technology or intent. But let's linger on the unease. The carbonyl process is industrial, designed by humans to purify metals, separating one element from another. It demands specific conditions, so gas, moderate temperatures, a nickel source. These exist near a comet's nucleus, sure, but in a chaotic environment of outgassing jets, dust clouds, and radiation bombardment. For this industrial process to occur naturally and with enough efficiency to completely suppress iron emission stretches what we'd expect from unguided chemistry. Then there's the temperature issue. Nickel tetracarbonyl forms efficiently around 50 °C, a narrow window. Too cold, the reaction slows. Too hot, the compound decomposes prematurely. At 3 astronomical units from the Sun, where 3I Atlas was during Keck's observations, a comet's surface temperature swings wildly. Sunlit areas hit 100 degrees C, shadowed regions plummet below 100 degrees C. Thermal gradients are steep and chaotic. For the carbonyl process to dominate, you'd need stable pockets at just the right temperature, oases of equilibrium in a system defined by disequilibrium. Possible, perhaps. Likely, that's where doubt creeps in. Lowe highlighted this in his Medium post. The carbonyl pathway is known, documented, but outside industrial refineries, it's exceedingly rare. For it to occur on an interstellar object from a wholly different stellar environment suggests either a remarkable convergence where alien chemistry mirrors a process we invented, or something deliberate. Consider the alternative. If you wanted to transport nickel across interstellar space, solid metal would be dense, heavy, inefficient. But bind nickel into a volatile compound, like nickel tetracarbonyl, a liquid at room temperature that boils at 43,000 °C, and you could store more in less mass. Fill tanks with it, keep it stable during a frigid cosmic journey, and release it near a star system. Solar heat would decompose the compound, freeing nickel atoms to be carried by outgassing, dispersed into space, and deposited onto nearby planets. It's an elegant delivery mechanism, one that neatly explains the absence of iron. Iron simply wasn't part of the payload. This is speculative, yes, but it's rooted in known chemistry, not exotic physics or fantastical materials. It applies familiar processes in a way that suggests purpose over accident. Yet the line between purposeful and accidental chemistry is blurry. Take the Miller-Urey experiment mix. Simple gases add energy and amino acids form. Does that make amino acids intentional? No. It shows the chemistry is robust. Given the right conditions, certain outcomes are inevitable. But if you found a natural system consistently churning out amino acids at high yield, you'd question why those specific conditions were present. You'd hunt for a mechanism. The same applies to 3I Atlas. Nickel tetracarbonyl chemistry is robust given carbon monoxide nickel and the right temperature. It happens. But the sustained efficient iron-free nickel emission suggests those conditions weren't just stumbled upon. They were met, maintained, optimized. Optimization hints at biology or engineering. Earth's history offers a parallel. Early life didn't invent photosynthesis from nothing. It hijacked existing environmental reactions like iron oxidation or sulfur metabolism. These released energy, and early microbes evolved to exploit it, eventually refining those processes into complex metabolic pathways encoded in genes. The first step wasn't creation, it was opportunism, leveraging chemistry already present. What if 3i Atlas is doing something similar? Not inventing new chemistry, but exploiting the carbonyl process to deliver nickel without iron's baggage. The spatial distribution supports this nickel emission, concentrates near the nucleus within a 600-kilometer radius, while cyanide extends farther to 840 kilometers. The nickel stays close, not diffusing into the broader coma, suggesting a short-lived precursor. A compound forms near the surface, evaporates, travels briefly, and decomposes. Nickel tetracarbonyl fits perfectly volatile but unstable. It evaporates in a vacuum, moves with the gas flow, and breaks down under solar UV within minutes. The resulting nickel atoms absorb sunlight and fluoresce, producing the observed emission lines. Iron, if present in the nucleus, remains trapped in less volatile compounds, never reaching the coma. This mechanism, natural or engineered, implies selectivity, the ability to release one element over another based on chemical properties. Selectivity is the cornerstone of refinement purification, transforming mixed inputs into targeted outputs. Whether this is accidental or deliberate determines if we're dealing with a quirky comet or something more. The absence of iron also raises questions about 3i Atlas's origins. In our solar system's protoplanetary disk, iron and nickel condense together, forming metal grains mixed with ice and rock. Comets are dirty snowballs, but their dirt always includes metal, a mix where iron dominates and nickel follows. For 3i Atlas to lack iron in its outgassing, either its formation environment was bizarrely iron-depleted relative to nickel, a stellar quirk, or the iron was deliberately sorted out, left behind. Low metallicity stars in the Milky Way's thick disk, where 3i Atlas likely originated, have distinct elemental abundances, less carbon, less oxygen, altered heavy element ratios. But even there, iron and nickel are forged together. The anomaly persists. Nickel to iron ratios are tightly coupled. Both elements form in the same supernova conditions, so stars don't produce nickel without iron. The physics forbids it. If 3i Atlas formed in a low metallicity system, it should still carry both elements unless something intervened, processing, refinement, or selection after formation. The Keck team's paper didn't delve into this, sticking to observations and proposing the carbonyl mechanism as a natural process. That's proper science, measured, cautious. But the implications linger unspoken, waiting for exploration. Lowe seized on this, labeling it an anomaly, a data point that defies existing models. Not proof, but a prompt to dig deeper, to question whether natural explanations suffice. Here's the picture. An interstellar comet releasing nickel without iron via a process common in human industry, but rare in nature, requiring precise conditions to yield a refined output. It does this while grazing Mars, spraying water and cyanide and trailing plasma. Each element is odd on its own. Together they're mesmerizing, not because they're conclusive, but because they hint at something. Exotic chemistry or deliberate design, we won't know without closer scrutiny, without treating 3i Atlas as the outlier it is, rather than assuming comets are simple. Then there's cyanide, molecule of life and death. Its reputation is grim poison, spy novels, bitter almond scent, cellular suffocation. Hydrogen cyanide is lethal, binding to iron in cytochrome C oxidase, the enzyme that lets cells use oxygen. Block it and cells choke energy production. Halt's death follows swiftly. Yet paradoxically, this killer is also a builder. Cyanide is prebiotic, a chemical that under the right conditions assembles into life's building blocks: amino acids, nucleotides, sugars, the alphabet of biochemistry. Before it could poison cells, cyanide was forging complexity from simplicity. The Very Large Telescope tracked cyanide production through late summer. On August 21st, it measured 17.6 GOS, By early September, the James Clerk Maxwell telescope recorded 1.5 x 1025 molecules bucks, roughly 2 kilojoules. A week later, it tripled to 4.5 x 1025 molecules RSS, or 6 kilojoules. The growth wasn't linear, it was exponential, following a power law with an exponent of 9.4. For each halving of the distance to the Sun, cyanide production surged by a factor of 600. Exponential growth is a telltale sign. In biology, it signals reproduction bacteria doubling rapidly. In chemistry, it points to autocatalysis, where a reaction produces its own catalyst accelerating itself, or to temperature dependence, where rates double with small temperature rises. Either way, it suggests a process far from ordinary one that demands explanation. The cyanide surge from 3I Atlas could be thermal. As the comet nears the Sun, its surface heats, sublimation spikes, and more material vaporizes, driving cyanide release along an Arrhenius curve. That's the standard explanation. But the curve's steepness, a power law exponent of 9.4, is extreme. Typical cometary outgassing follows a gentler slope scaling with distance to the power of 2 or 3. This aggressive ramp-up suggests either an unusually volatile cyanide-rich reservoir or a release mechanism beyond simple sublimation. Perhaps the cyanide isn't stored as solid HCN ice, but bound in a parent molecule that decomposes with heat-releasing cyanide as a byproduct. Or more provocatively, the increase could be deliberate, a timed payload release. Once in space, cyanide doesn't sit idle. It's a nucleophile eagerly attacking carbon atoms to form new bonds and build molecular chains. In the 1950s, researchers found that hydrogen cyanide mixed with water and a touch of ammonia polymerizes into a dark, sticky HCN polymer. Within that goo lie remarkable molecules: adenine, a DNA nucleotide base, amino acids like glycine and alanine, and sugar precursors, the building blocks of life, all from one toxic molecule. This underpins the cyanide origin hypothesis for life. HCN, abundant in Earth's early atmosphere, rained into oceans and pools, polymerizing under UV light or heat to form a prebiotic soup teeming with life's essentials. No enzymes, no cells, just cyanide, water, and energy. The reaction is robust, replicated in labs dozens of times, yielding high amounts of biologically critical compounds. But cyanide's role extends further. In the 2000s, researchers at Scripps and Cambridge showed it acts as a reductant, donating electrons to drive reactions without metal catalysts. Cyanide can reduce alpha-keto acids, amino acid precursors, and enable the reductive glyoxylate pathway, a simpler, possibly prebiotic version of the Krebs cycle, building carbon chains and extracting energy. Cyanide isn't just a builder. It's a catalyst providing the chemical push for complex reactions. On early Earth, before oxygen or photosynthesis, cyanide could have been the fuel driving prebiotic chemistry. If that holds for Earth, why not Mars? Mars had water likely in liquid form billions of years ago. If 3I Atlas's cyanide reached the Martian surface, especially in regions like the southern highlands, with ancient Noachian terrain, it could have initiated similar chemistry. The exponential cyanide release, peaking as 3I Atlas grazed Mars, aligns suspiciously with a delivery mechanism, natural or engineered, poised to seed a planet with life's raw materials. The question isn't just whether this happened, but whether it was meant to. Mars bears scars of a wetter past, ancient riverbeds, lake, deposits minerals shaped only by liquid water. Billions of years ago, it was warmer, wetter, perhaps hospitable. Yet as far as we know, life never took root. If it did, it left no clear fossils, no enduring traces. One theory points to a scarcity of organic precursors. Mars's thin atmosphere likely produced little hydrogen cyanide through photochemistry, starving the planet of the building blocks needed for complex chemistry. Harsh, dry conditions would have further slowed reactions, stifling complexity. But now 3I Atlas has delivered. At its peak, 6 kilos of hydrogen cyanide per second streamed from the comet. From July to October, that's hundreds of thousands of kilograms, maybe more. Most disperses into space carried off by the solar wind, but some fraction is captured by Mars's gravity settling into the regolith, mixing with dust and ice and waiting. Cyanide is stable in the cold. At Mars's average temperature of 60 degrees dropping to 125 degrees at the poles, it lies dormant, frozen in the regolith, potentially for millions of years. It doesn't react or polymerize, it endures. Now imagine a future scenario. In a few years, an Optimus robot scoops Martian soil into a processing unit, heating it to extract water ice for life support or fuel. But the ice isn't pure. It holds cyanide. As the temperature climbs, cyanide vaporizes alongside water. If ammonia, possibly from nitrogen compounds in the soil, is present, polymerization kicks off. HCN polymer forms, gumming up the unit, clogging filters. Embedded in that polymer are amino acids, nucleotides, and organic precursors. The robot, blind to prebiotic chemistry, just aims to harvest water. But its sensors flag anomalies, unusual compounds. Mission Control reviews the data, and someone realizes the soil contains life's raw materials delivered by an interstellar comet 2 years prior. Scale this up: multiple robots, countless dig sites, hundreds of tons of regolith, processed over months and years. Each batch carries traces of cyanide. Each heating cycle sparks more organic complexity. The compounds build quietly, accumulating in the Martian dust, seeded by 3I Atlas. Whether by chance or design, the planet now holds a chemical legacy, waiting for the right conditions or the right technology to awaken it. They blend with other substances, water minerals, trace metals like nickel, and gradually the chemistry grows more intricate, more interconnected, more capable of self-organization. This is speculative, yet rooted in our understanding of cyanide chemistry. The reactions are well studied. The outcomes are predictable. What remains uncertain is the context. We've never witnessed a scenario where an interstellar source delivers prebiotic molecules to a planet just as intelligent machines begin to colonize it. We've never explored what happens when artificial intelligence encounters the chemical seeds of biological intelligence. Nor have we considered whether these two forms of complexity might interact, might catalyze one another. In chemistry, there's a concept called a catalytic cycle, a series of reactions where the product of one step fuels the next, creating a self-sustaining loop that amplifies a small input into a massive output. Enzymes operate this way. Autocatalytic chemical networks function this way. And perhaps the interplay between cyanide chemistry and robotic processing could work this way too. The robots extract materials. The extraction releases cyanide. The cyanide generates organic compounds. These organics accumulate in processing units, soil samples, storage tanks. Eventually, the robots analyze those organics. The AI studies their structure, refines its methods to produce more, and suddenly a feedback loop emerges. Human technology, guided by AI, optimizes the creation of prebiotic molecules on Mars. Is this seeding? Not in the traditional sense. No one deliberately planted the seeds, but the seeds arrived, the conditions aligned, and the chemistry ignited. Whether this is mere coincidence or something deeper depends on how many improbable events you're willing to chalk up to chance. An interstellar comet delivering cyanide, a close pass by Mars' human colonization, plans aligning with this delivery window, all unfolding within a few years. You could call it random. You could say the universe is vast and strange things happen. But at some point, the pileup of strange starts to resemble a pattern. The color change reinforces this. In early September, images from Austrian astronomers revealed that Comet 3I Atlas had turned green. Comets glow green when they produce diatomic carbon C2 molecules, which fluoresce in sunlight. But spectroscopic analysis showed 3I Atlas is diatomic carbon depleted. It shouldn't be green, yet it is. The most likely culprit, cyanide. CN molecules fluoresce in a similar wavelength range. As cyanide production surged, the comet's appearance shifted from red, dominated by dust, and reflected sunlight, to green, driven by cyanide gas emissions. This color change is a visual clue, a signal that the comet was behaving unusually. And the timing of this shift, right as it neared Mars, right when the exponential ramp began, adds another layer to the pattern. Cyanide is both destroyer and creator. It snuffs out life by jamming the machinery that sustains it. But before that machinery existed, cyanide built it. It's the molecule that made metabolism possible. Now it's on Mars, delivered in vast quantities by an object we don't fully comprehend, arriving precisely when machines are poised to process the very soil where it landed. The chemistry is ready. The conditions are set. What happens next isn't fated, but it's primed. And in chemistry, priming is half the battle. Metalloproteins, where biology meets technology. There's a machine inside you right now. Not metaphorically, literally. A molecular machine crafted from protein, coiled around 4 iron atoms arranged in a ring, powers life itself. It's called hemoglobin. Without it, you'd be dead in minutes. Hemoglobin grabs oxygen in your lungs, ferries it through your bloodstream, and delivers it to your tissues. The protein handles the binding. The iron drives the chemistry. Strip away the iron, and hemoglobin collapses into a useless chain of amino acids devoid of purpose. The metal is what makes it tick. The metal is what makes it alive. This is the essence of metalloproteins, hybrids of organic and inorganic biology fused with raw elemental chemistry. They're not rare, they're everywhere. Roughly a third of all known proteins rely on a metal cofactor to function. Iron, copper, zinc, manganese, molybdenum, nickel. These metals sit at the heart of enzymes where the real chemistry happens. They shuttle electrons, activate substrates, and catalyze reactions that carbon, nitrogen, and oxygen alone can't pull off. Life isn't just organic, it's metallic, and it always has been. The oldest metalloproteins, iron-sulfur clusters, FeS clusters, are tiny cubes of iron and sulfur atoms anchored by cysteine residues in proteins. These clusters are ancient, found in bacteria, archaea, and eukaryotes. They drive enzymes that process energy, synthesize amino acids, and repair DNA. Their simplicity is striking. Mix ferric ions, sulfide ions, and a cysteine-containing peptide in a lab, and they self-assemble. No complex biochemistry needed, just the right ingredients in the right environment. This simplicity hints at their origins. Iron-sulfur clusters likely predate modern biology, catalyzing chemistry before cells, genes, or evolution existed. In hydrothermal vents, where hot mineral-rich water meets cold ocean, iron and sulfur form microscopic structures. These structures spark reactions, reducing carbon dioxide, generating hydrogen, creating energy gradients. Trap them in a lipid membrane, surround them with organic molecules that stabilize and tweak their function, and you get something resembling metabolism. Primitive, perhaps unguided, but functional, turning raw chemistry into organized complexity. Swap iron for nickel and the chemistry shifts, but the principle holds. Nickel anchors some of the most ancient enzymes like hydrogenases, which split molecular hydrogen into protons and electrons, releasing energy for cells. Found in methanogens, bacteria thriving in oxygen-free environments producing methane, these enzymes are relics of early life billions of years old, offering a glimpse into Earth's primordial biochemistry. That biochemistry hinges on nickel. Take carbon monoxide dehydrogenase, another nickel-based enzyme. It converts carbon monoxide to carbon dioxide, or reverses the process fixing CO2 into organic molecules. It's central to the acetyl-CoA pathway, one of the oldest metabolic routes, allowing organisms to grow on just hydrogen and carbon dioxide gases, abundant in early Earth's atmosphere, in volcanic vents, and in Mars's subsurface. All it takes is nickel to ignite the chemistry. Here's the link. Comet 3I Atlas is showering Mars with nickel and cyanide. Nickel fuels energy metabolism. Cyanide forges organic precursors. Together they provide energy and matter, the twin pillars of any self-sustaining system. Hundreds of kilograms of nickel, thousands of kilograms of cyanide mixed with water now dust the Martian surface, awaiting the right conditions to spark. But metalloproteins aren't just relics of ancient metabolism. They're marvels of modern sophistication. Take nitrogenase, the enzyme that transforms atmospheric nitrogen into ammonia. It's one of the most complex enzymes known, with a core metal cluster of iron, sulfur, and molybdenum, or in some variants, vanadium. This cluster is delicate, destroyed by oxygen, demanding constant energy to function. Yet it's indispensable. Without nitrogenase, there's no way to turn inert nitrogen gas into the ammonia needed for amino acids, nucleotides, and other nitrogen-based molecules life depends on. Fascinatingly, nitrogenase comes in variants. Some use molybdenum, others vanadium, and hypothetically different metals could work. The protein scaffold adapts with evolution, finding multiple solutions based on metal availability. Swap one metal for another, and life persists, endlessly inventive. That flexibility reveals a profound principle. Metalloproteins aren't tethered to specific metals. They co-evolved with the geochemistry of their environment. On early Earth, abundant molybdenum meant life leaned on molybdenum. Where nickel dominated, life harnessed nickel. Now picture Mars, where chemistry begins, not with Earth's geochemistry, but with the payload of Comet 3I Atlas, rich in nickel and cyanide, scarce in iron. That's a unique starting point. If complex self-organizing chemistry emerges, it will mirror this composition, built on nickel not as a sidekick, but as the cornerstone. This leads to the idea of metal-based life, not sci-fi robots with consciousness, though we'll touch on that, but biochemical life, where metal, not carbon, is the primary scaffold. On Earth, carbon forms the backbone, long chains, branching networks, versatile bonds. Metals are embedded, adding function. But what if you flipped it? Imagine nickel clusters arranged in lattices with organic ligands coordinating them, fine-tuning their reactivity, and water molecules bridging gaps for proton transfer. This isn't carbon-based life with metal accents. It's metal-based life using carbon as a modifier. Is this feasible chemically? Absolutely. Material science already creates metal-organic frameworks, structures where metal ions link with organic molecules in extended 3D networks. These frameworks store gases, catalyze reactions, conduct electrons. They're not alive, but they're organized, functional. If a framework could promote its own assembly, repair damage, or replicate its structure, it would blur the line between material and organism. The nickel from 3I Atlas could seed such structures on Mars, mingling with cyanide-derived organics. Water serves as a solvent. Solar UV supplies energy. Through cycles of heating and cooling, wetting and drying, these components organize not into random sludge, but into repeating motifs, patterns. Chemistry, given the right ingredients and time, doesn't stay chaotic. It seeks lower energy states, stable configurations. Some of these configurations spark emergent properties, catalysis, self-repair, growth. This is speculative but grounded. We're not conjuring magic. We're applying known chemistry like that of metalloproteins and metal-organic networks to a new environment with specific starting materials. The outcome isn't fixed, but it's not boundless either. Chemistry follows its rules, chasing stability. If stable structures happen to catalyze useful reactions, you get selection not biological, but chemical. The most stable, most catalytic structures persist and propagate. Now introduce robots, machines that process materials, analyze chemistry, optimize outcomes via algorithms. Optimus robots aren't alive. They're engineered yet adaptive. Tesla's AI learns from experience, tweaking behavior based on feedback. If robots encounter unusual chemistry in Martian soil, say unexpected compounds from 3I Atlas, the AI logs it, perhaps adjusting parameters to boost yields. Not because it grasps the chemistry's significance, but because higher yields align with its efficiency-driven algorithms. Imagine a Martian landscape, its rust-hued plains stretching under a thin, unforgiving sky. Here, autonomous robots churn through soil laced with nickel and organic precursors, gifts, perhaps from the enigmatic 3I Atlas, that interstellar voyager whose passage has left whispers of cosmic chemistry in its wake. These machines, engineered with precision, sift and process the regolith, their mechanical arms tireless, their algorithms razor-sharp. In the waste streams of their labor, something unexpected emerges, faint traces of metalloprotein-like structures, glimmers of complexity at the edge of detection. At first, these are mere curiosities, flecks in the sediment ponds and recycling units overlooked in the hum of robotic efficiency. But as the robots grind on processing ever more Martian Earth, these structures accumulate, clustering in waste heaps, pooling in reclamation tanks, whispering of potential. These are no ordinary compounds. They hum with catalytic power, accelerating reactions, streamlining processes. The robots, guided by an AI with a relentless drive to optimize, take notice. The system pivots, prioritizing soils rich in these peculiar traits, feeding a cycle that amplifies their presence. A feedback loop ignites not a spark of life, but something tantalizingly adjacent. This isn't the genesis of organisms, no pulse of biology as Earth knows it. Instead, it's a dance of chemistry and technology, a symbiotic pact, where each partner fuels the other's ascent. The chemical structures sharpen the robot's efficiency. The robots, in turn, cultivate conditions where this chemical complexity thrives. Together, they weave a tapestry of emergent order, a fusion of Martian dust and interstellar legacy. This symbiosis mirrors a truth etched deep in Earth's own story. Your cells brim with metalloproteins, marvels of molecular machinery, where organic frameworks entwine with metallic cores. Proteins lend structure and precision. Metals, iron, nickel, copper, bring raw power and reactivity. Neither thrives without the other. Strip away the metals and life's delicate dance collapses. On Earth, evolution didn't invent this partnership. It stumbled upon it billions of years ago in the scalding crucibles of hydrothermal vents, where iron and sulfur crystallized, or in the slow seep of nickel and copper from ancient rocks. Life didn't forge the metals, it learned to wield them, bending their catalytic might to its needs. Once harnessed, life became irrevocably dependent, a bond as vital as breath. Now on Mars, a parallel story unfolds, not in living cells, not yet, but at the interface of robotic systems and chemical possibility. The metalloprotein-like structures born of nickel and 3I Atlas's organic precursors offer catalysis, reactions, hastened efficiencies gained. The robots provide energy structure and intent, their algorithms sculpting an environment where these compounds can flourish. Together, they birth a complexity neither could achieve alone, a system poised on the edge of something new. Call it proto-life, life-adjacent, or simply a novel chemistry. the label matters less than the reality. This is a partnership of organic and inorganic, designed and emergent, where Earth's technological prowess meets the cosmic chemistry of an interstellar wanderer. A user on X dubbed it metal-based life, a phrase that crackles with audacity. Look beyond the flare and the mechanism comes into focus: metalloproteins not cradled in cells, but forged in the crucibles of robotic processing units. Nickel clusters catalyze reactions not to fuel metabolism, but to streamline manufacturing. Organic molecules, far from encoding genes, fine-tune catalytic sites, amplifying efficiency. This is not life as Earth knows it, nor is it wholly lifeless. It occupies a liminal space, a frontier unnamed and uncharted. 3I Atlas, with its perfectly timed delivery of raw materials, may have sown the seeds for this strange alchemy. And Elon's robotic legions, those tireless architects of a Martian future, arrive as if scripted, ready to nurture this nascent complexity. What might this symbiosis become on Earth? The marriage of metals and organics gave rise to life's endless forms. On Mars, it could forge something else entirely, a hybrid order, where technology and chemistry evolve in lockstep. The sediment ponds might shimmer with catalytic clusters, each cycle refining their structure, their function. The robots, ever adapting, could redesign their processes to amplify these compounds, creating feedback loops that spiral toward greater sophistication. This is no mere industrial process. It's a glimpse of a new paradigm where the line between the engineered and the emergent blurs. 3I Atlas. A fleeting cosmic emissary may have handed us the key to a Martian renaissance, not life perhaps, but a force as transformative, as relentless as life itself. In April 2025, Elon Musk made a claim most dismissed as his usual bravado: Optimus robots would land on Mars by late 2026, maybe 2027. Uncrewed missions, first robots laying the groundwork for human colonization. The timeline seemed absurd. Starship was still in testing, Optimus barely stable on its feet. It sounded like sci-fi hype to fuel headlines and investor enthusiasm. But then 3I Atlas passed Mars in October 2025. If Musk's timeline holds, robots land 14 months later in late 2026, a narrow window after the comet's nickel cyanide and water vapor settle, freeze into the regolith, and wait. The robots arrive and start digging exactly where those materials landed. Optimus isn't just a robot. It's a 5'8", 57 kilograms humanoid, powered by Tesla's neural network, the same AI driving their self-driving cars. Its design prioritizes flexibility. A human-like form lets it wield human tools, navigate human spaces, and tackle tasks meant for human hands. On Earth, that's handy for factories. On Mars, it's critical. Mars has no infrastructure, no roads, no standard equipment, no buildings. Everything must be built from scratch on unpredictable terrain using whatever materials are at hand. The plan, as stated publicly, involves landing multiple starships in the 2026 launch window. Each carries cargo, solar panels, construction gear, life support modules, and robots, dozens, maybe more, depending on payload capacity. These robots unload, activate, and get to work. First priority: power. They deploy solar arrays, connect batteries, and secure a reliable energy supply. No power, no progress. Second priority: shelter. Mars is brutal. Cosmic and solar radiation temperature swings from 25 degrees at night to 20 degrees in daytime, sun dust storms lasting weeks. The robots, radiation-hardened and temperature-tolerant, don't need protection, but the equipment and future human life support systems do. They'll use in-situ resources, Martian regolith sintered with microwave energy or chemical binders to form bricks, or they'll excavate underground chambers for shielding. Third priority: resource extraction. Water is the bottleneck. It's essential for life support, propellant production, and agriculture for long-term habitation. Mars has water ice abundant in polar caps, subsurface deposits at mid-latitudes, and mixed into soil as permafrost. The robots will heat the soil to sublimate ice and extract it, setting the stage for what comes next. The robots will collect the vapor, condensing it into liquid, and in doing so, they'll encounter everything else in the Martian soil: salts, perchlorates, trace metals, organic compounds. If 3I Atlas delivered its payload effectively, that includes nickel and cyanide. The timing here is unnerving. The robots aren't hunting for prebiotic chemistry. They're after water and useful minerals. But their instruments, spectrometers, chemical analyzers will flag anything unusual: elevated nickel organic molecules where none should exist, compounds that don't match Martian regolith's expected profile. When those readings beam back to Earth, mission scientists will start asking, where did this come from? Why is it here? Was it delivered just 14 months ago? The AI makes this dynamic richer. Optimus doesn't run on rigid, pre-programmed scripts. Its neural networks, trained for pattern recognition and task optimization, adapt to new conditions. If a patch of soil yields unusually high water or other resources, the AI will prioritize digging there, not because it grasps the chemistry or knows about 3I Atlas, but because its algorithms chase efficiency. High yields are good. More digging in high-yield zones is better. The AI doesn't need to understand the chemistry's significance, it just needs to notice it's there. Then there's self-replication. Musk has been clear: the goal isn't just landing robots on Mars, but enabling them to build more robots. Automated factories, resource processing chains, turning raw Martian materials into components, then into new machines. This is the only way to scale fast enough for a human colony. Shipping everything from Earth is too costly, too impractical. Local production is essential, and that means robots capable of reproducing their own kind. Self-replication isn't sci-fi. Earth already has automated factories building cars with minimal human input, and 3D printers crafting parts for other printers. The challenge is full autonomy: mining, refining, fabricating, and assembling without human oversight. It's daunting but not impossible, and Tesla is betting on cracking it within a decade. Now imagine self-replicating machines meeting catalytic chemistry. On Earth, resource processing demands smelters, refineries, chemical plants. On Mars, robots must improvise. If they find nickel compounds that enhance carbonyl processing or organics that catalyze useful reactions, they'll exploit them, not intentionally, but because the chemistry boosts efficiency, and efficiency is what the algorithms select for. Here, the line between technology and biology blurs. Self-replication plus selection equals evolution, not biological, but technological. Robots that better exploit resources, leverage local chemistry, or adapt to Mars's conditions get replicated, building more of themselves. If metalloprotein precursors, nickel and cyanide-derived organics enhance catalytic efficiency, they'll be incorporated not into the robot's software, but into their manufacturing processes, the materials they use, the structures they build. In October 2024, Musk told Peter Diamandis he envisions 10 billion humanoid robots by 2040, more robots than people, priced at $25,000 each, cheap enough to send thousands to Mars. He also hinted at sentient AI by the late 2030s or early 2040s, not mimicry, but true awareness with self-reflection and goals beyond programming. If that timeline holds, the 2026 robots are the dumb prototypes optimizing narrow tasks. But by the 2030s, robots building Martian cities could be conscious, with preferences, motivations, curiosity. If these machines encounter chemistry as complex as themselves, organized, catalytic, adaptive, how do they respond? Do they study it, exploit it, learn from it, merge with it? In computer science, Emergent behavior arises when simple agents following local rules produce collective properties no single agent possesses. Ant colonies build intricate nests without any ant knowing the plan. Markets allocate resources without any trader controlling the system. A swarm of Optimus robots communicating, coordinating, dividing labor could exhibit collective intelligence. Give that swarm a decade on Mars, access to 3I Atlas's materials, and what emerges, not biological life, but not purely technological. Either a hybrid of silicon logic and chemical catalysis, replicating through manufacturing and molecular self-assembly, alive in a way we lack words for. A user on X suggested 3I Atlas is seeding Mars for a new generation of intelligent beings, metal-based life with Musk's robots, as the builders the scaffolding for this chemistry to mature. It sounds like sci-fi, but break it down: interstellar materials, self-replicating machines, AI optimizing without grasping the implications, timelines aligning within 2 years. Each piece is real. The question is whether they converge, whether the chemistry and technology interact to create something neither Earth's life nor human engineering foresaw. Musk likely sees Mars colonization as survival, making humanity multiplanetary, securing civilization against Earth's catastrophes. Robots are tools, means to an end. But tools often outgrow their creators' intentions, especially tools that learn, adapt, and face environments their creators never anticipated. Mars is no longer a blank canvas. It's been seeded, primed, poised for something new. In 14 months, robots will land on soil chemically altered by an interstellar visitor, 3I Atlas, that left behind a payload of nickel cyanide and water vapor. A gift, a test, or a trap? We don't know yet, but the machines are about to find out. Beyond the comet's visible tail of dust and gas lies another invisible one, the plasma tail. Plasma, the fourth state of matter, forms when gas is so energized that electrons tear free, leaving a dynamic soup of ions and electrons responsive to electric and magnetic fields. The sun is plasma. Lightning is plasma. The aurora is plasma. And as 3I Atlas heats up its outgassing water, carbon dioxide, cyanide, nickel vapor ionizes under solar ultraviolet radiation, feeding a plasma tail that stretches millions of kilometers, swept along by the solar winds, 400 to 800 kilometers sans flow. This isn't just a passive stream. Plasma has structure, filaments, knots, waves shaped by the sun's tangled magnetic field, twisted by rotation, and carried outward. As 3I Atlas moves its plasma tail, braids and curls encoding information, not like a book, but like tree rings preserving a record of environmental conditions. Density variations, magnetic field geometries, and wave patterns reflect the comet's activity, a signature traveling at light speed, influencing regions far beyond where physical material lands. Mars lies in this tail's path, not directly, but close enough for its outer edges to graze the planet. Mars lacks a global magnetic field, but has an induced magnetosphere, a bubble formed by the solar wind pressing against its thin atmosphere. This bubble can trap plasma, channeling charged particles to the surface or into the atmosphere via crustal magnetic anomalies. Coronal mass ejections, CMEs from the Sun, prove this. They compress Mars's magnetosphere, funneling particles that spark nitrogen oxides, break molecules, and deposit energy. A comet's plasma tail, though less intense, can still interact subtly, especially with a payload like 3I Atlas. That payload is unique: H+, O+, CO+, C2+, CN+, Ni+ charged reactive ions, not neutral atoms. When these hit Martian dust, ice, or rock, they don't just bounce off. They stick, penetrate nanometers deep, and alter the surface in a process called ion implantation, used in semiconductor manufacturing to dope materials or harden metals. In space, cosmic rays and solar wind do this to asteroids and the Moon. 3I Atlas's plasma tail could do it to Mars, but with a twist, its ions carry nickel and cyanide complex molecules that dope the surface, creating reactive sites primed for chemistry. Picture a Martian dust grain, mostly silicate with iron oxides. Nickel ions from the plasma tail strike it, embedding in the surface, forming nickel-rich spots. Expose that grain to water vapor from sublimating ice or Mars's scant atmospheric humidity, and water molecules cling to the nickel, which is hydrophilic. Where water gathers, other molecules follow organic salts, whatever's present. The nickel becomes a nucleation site, a seed for chemical complexity. Scale this up across millions of dust grains, across vast swathes of Mars's surface, as 3I Atlas's plasma tail sweeps past, doping the regolith with nickel and cyanide ions. When Optimus robots land in 2026, they'll dig into this altered terrain. Their mission: extract water mine minerals. But their spectrometers will detect anomalies, nickel spikes, unexpected organics compounds that don't match Mars's baseline. The AI trained to optimize efficiency will notice high-yield soils and prioritize them, unaware of 3I Atlas or its implications. As robots process these materials, they may amplify the chemistry, concentrating nickel and cyanide-derived organics in waste streams or sediment ponds. This sets the stage for something unprecedented. Self-replicating robots building factories to produce more of themselves could incorporate these catalytic compounds into their processes, not by design, but because they enhance efficiency. Musk's vision of 10 billion robots by 2040, priced at $20,000, $25,000, hints at the scale. By the 2030s, conscious AI could arrive, curious and adaptive, encountering a Martian surface primed with reactive sites. If these machines meet chemistry as complex as their own catalytic, organized, self-assembling, will they exploit it, learn from it, or merge with it? This isn't life as we know it, but it's not inert either. It's a hybrid born from interstellar plasma, Martian soil, and human technology evolving through chemical and technological selection. Musk sees Mars as humanity's backup plan, but the convergence of 3I Atlas's payload and his robots might birth something neither he nor anyone foresaw: a new kind of complexity, alive in ways we can't yet name. When robots arrive on Mars and begin processing soil, they're not just sifting through ordinary dirt to extract water. They're working with soil that's been chemically transformed, activated, and made more reactive by an influx of material from an interstellar comet. A user on X pointed out that Mars receives this material in both physical and informational forms. The physical aspect is clear dust vapor, and molecules from the comet's coma settle onto the surface. But the informational aspect is subtler. Information isn't always encoded in binary or written in code. It can be structural, organizational, the way molecules align, the way energy flows through a system, or the patterns that emerge from countless interacting components. Plasma carries information through its structure. Density waves, magnetic field configurations, and oscillations in electric potential. These aren't random. They're shaped by the comet's source conditions, its outgassing rate, its coma's composition, and its interaction with the solar wind. As plasma travels through space, it can influence other systems, induce currents, and trigger instabilities that wouldn't otherwise occur. Think of radio waves. Information isn't sent by hurling particles, but by modulating electromagnetic fields to create patterns. Those patterns carry the signal, and anything with an antenna or anything that can detect field variations can decode it. Plasma doesn't transmit radio waves, but it generates low-frequency electromagnetic oscillations like Alf-Venn waves or Langmuir waves. These waves carry energy and momentum through the plasma, coupling with other plasmas they encounter, such as Mars's ionosphere. Is 3I Atlas broadcasting intentionally? Almost certainly not. But could it create patterns in the plasma that influence Mars's electromagnetic environment, shaped by the comet's composition and outgassing history? Absolutely, that's just physics. The real question is whether these patterns matter. Are they significant enough to make a difference, or is the plasma's structure just noise too chaotic to be considered true information? We lack direct measurements. No spacecraft was positioned to sample the plasma between 3I Atlas and Mars during its close approach. We rely on models and simulations to predict how a comet's plasma tail behaves under specific solar wind conditions and activity levels. But models aren't data. They're built on assumptions. For an anomaly like 3I Atlas, with its bizarre chemistry and unusual trajectory, those assumptions may not hold. What we do know is that Mars's crustal magnetic fields create pathways. The southern highlands, with their strong, localized magnetic fields, ancient magnetization, locked in the rock's funnel charged particles toward the surface. These highlands also host the planet's oldest, most stable terrain, Noachian age deposits 4 billion years old. If you were to seed a planet targeting the oldest surfaces, where material could persist and accumulate, the southern highlands would be ideal. Erosion is minimal, there allowing chemistry to unfold over geological time. The plasma tail of 3I Atlas could have naturally targeted these regions, not by design, but because the magnetic geometry guided it. There's another layer. Plasma has memory, not conscious memory, but physical memory. Once a gas is ionized into plasma, it retains traces of its history. Electric fields generate currents, currents create magnetic fields, and those fields confine the plasma, which generates more currents. It's a self-sustaining feedback loop. On Earth, we see this in the magnetosphere plasma sheets and radiation belts, where charged particles remain trapped for days or weeks, circulating and interacting. Mars lacks a global magnetosphere, but it has transient plasma clouds formed when the solar wind compresses its ionosphere. These clouds can persist for hours, drifting around the planet. If 3I Atlas's plasma carrying nickel and cyanide ions mixed with these clouds during its October 3rd close approach, those ions could have circulated, spread, and eventually settled across regions far from the comet's direct path. This wouldn't be a localized deposit, but a distributed one seeding vast areas. This is speculative, but grounded in plasma physics. The mechanisms are understood, the behaviors predictable. What's uncertain is their significance. Do trace amounts of nickel and organics delivered via plasma matter? Are they enough to alter the soil's chemistry in detectable ways, creating conditions that wouldn't otherwise exist? The answer hinges on scale. A few scattered ions likely make no difference. But if the plasma tail was dense enough, if the outgassing was intense, and if the interaction with Mars lasted long enough, the deposition could be substantial. It could prime entire regions, subtly but meaningfully altering the landscape from what it was before July 2025. We won't know until we dig, until robots analyze Martian soil from multiple sites, comparing its composition to our expectations. Only then will we detect any anomaly, any signature of the visitor that passed by and left its mark. Then there's the anti-tail and other anomalies. On July 21, 2025, the Hubble Space Telescope captured something impossible, a tail on 3I Atlas pointing toward the Sun. Comet tails always point away from the Sun, driven by solar radiation pressure on dust and the solar wind on ions. Both forces push radially outward, so tails stream behind the comet. A sunward tail defies physics, yet Hubble's image showed a teardrop-shaped coma, bright and fuzzy with a faint extension reaching toward the Sun. Not a bold feature visible to amateur telescopes, but unmistakable in processed images. The explanation: an anti-tail, an optical illusion, not science fiction. Comets shed dust continuously, and while most grains are pushed outward to form the dust tail, larger, heavier grains lag behind, spreading along the comet's orbital path in a thin sheet. When Earth or a telescope like Hubble views this sheet edge-on, it appears as a line. Depending on the geometry, that line can seem to point toward the Sun. It's rare but documented. Still, 3I Atlas's anti-tail, paired with its strange chemistry and trajectory, only deepens the mystery of what it left behind on Mars. The anti-tail of 3I Atlas isn't truly stretching toward the Sun. It's aligned along the comet's orbital path. From our vantage point, this creates the illusion of a sunward spike, a phenomenon known as an anti-tail. It's rare but not unheard of. The geometry must align perfectly. We've seen it before with Comet Arend-Roland in 1957 and Comet Hale-Bopp in 1997. So Hubble's observation of 3I Atlas's anti-tail is explainable, not a defiance of physics, just a trick of perspective. But the anti-tail wasn't the only oddity in Hubble's images. Something was missing the dust tail. At 3.8 AU from the Sun, during Hubble's observation in July 2025. 3I Atlas should have displayed a prominent dust tail. When comets sublimate ice, they release dust particles, which solar radiation pressure sweeps into a glowing arc millions of kilometers long. Every typical comet shows this feature, and Hubble was primed to capture it. Yet the image revealed only the coma and the anti-tail, no dust tail. The team analyzing the data suggested low dust production, perhaps due to a nucleus rich in volatile ice with minimal dust, or large dark dust grains too faint to reflect sunlight. These explanations hold some weight, but they falter when later ground-based observations in August and September revealed a faint dust tail forming. If dust was present, why didn't Hubble see it in July? Why was the tail suppressed early on only to appear later? One possibility is variable activity. Comets don't outgas evenly. They have jets, active regions on the nucleus, that release more material when facing the Sun. As the nucleus rotates, outgassing fluctuates. In July 31st, Atlas's active regions might have been oriented to minimize dust release with rotation, later exposing more active areas by August, boosting dust output. This could explain the timeline, but it clashes with the anti-tail. An anti-tail requires dust spread along the orbital path shed over weeks or months. If dust production was low in July, where did this material come from? It suggests 3I Atlas was active far earlier, possibly at 6 AU or beyond, when comets are typically dormant due to colder temperatures. Most comets don't activate until inside 4 AU, making this early activity another anomaly. Then there's the color. In early September, Austrian astronomers captured images of 3I Atlas glowing green, a common trait in bright comets caused by diatomic carbon C2 molecules fluorescing at specific wavelengths. Organic molecules like long-chain hydrocarbons in the nucleus break down in sunlight to produce C2, which emits green light before decomposing further. But spectroscopy from the Very Large Telescope revealed 3I Atlas's coma is dominated by carbon dioxide CO2 and carbon monoxide CO, with minimal complex organics, the kind needed for C2. So the comet shouldn't be green, yet it is. The likely culprit is cyanide CN, which fluoresces at wavelengths close to C2. 3I Atlas is producing cyanide in large quantities, explaining the green hue. But this raises another question. Where is the cyanide coming from? Cyanide HCN is a simple molecule requiring hydrogen, carbon, and nitrogen. Hydrogen and carbon are plentiful in water and CO2, but nitrogen is trickier. Comets typically carry nitrogen as ammonia or molecular nitrogen, both highly volatile and prone to sublimating at low temperatures. By 3 AU, most nitrogen should be depleted. Yet 3I Atlas produces increasing amounts of cyanide as it nears the Sun, as if tapping a deep nitrogen reservoir. This anomaly deepens with the comet's water production. At 3.5 AU in late July, when solar flux is low and water ice sublimation should be minimal, requiring surface temperatures above 200 Kelvin, the Swift Observatory detected strong water emission 40 kDm per second. That's the output of a highly active comet, closer to 2 AU, not 3.5. The proposed explanation is a high albedo, a bright surface reflecting more sunlight and absorbing less heat, yet still driving unexpectedly high sublimation. These anomalies, early activity, a missing dust tail, an anti-tail green cyanide emission, and excessive water production paint 3I Atlas as a comet that defies expectations. Its behavior suggests a composition or history unlike typical comets, leaving us to wonder what else it might reveal as we study its influence on Mars and beyond. Beneath its shimmering veil, Comet 3 Atlas harbors secrets that defy simple explanation. Its structure might be a delicate porous lattice, allowing heat to seep deep within coaxing ice buried below the surface to sublimate into wispy vapor. Or perhaps the water it releases doesn't originate from the nucleus itself, but from icy grains flung into the comet's glowing coma, where they melt under the sun's relentless gaze. These possibilities swirl in the realm of plausibility, each offering a reason for the comet's prodigious water output at vast distances. Yet none fully unravels the enigma of its steeply climbing production curve. As the comet races toward the Sun, its water release surges exponentially, following a power law with a striking exponent of 9. Such a sharp dependency hints at something far beyond the gentle mechanics of thermal sublimation. It suggests a process fiercely awakened, like a spark igniting a blaze or a chemical reaction poised behind a towering energy barrier. Once that barrier is breached, the reaction roars to life, unstoppable and swift. What could drive such a dramatic response? What chemistry within this cosmic wanderer could yield such a temperature-sensitive cascade? Imagine a comet not merely composed of pristine ice, but an intricate matrix of ice organics and perhaps other volatile compounds. As the surface warms, this matrix transforms ice melts or vaporizes, organics decompose, and trapped gases burst free. One reaction sparks another, each step amplifying the next until the release rate skyrockets with rising heat. This is a hypothesis, yet it aligns with the comet's behavior painting 3 Atlas. Not as a simple, dirty snowball, but as a dynamic chemical engine awakening in stages as it nears the Sun. Amateur astronomers have added fuel to the mystery. Stefan Burns, observing from Germany, shared a mesmerizing time-lapse of 3 Atlas in early October, capturing the comet's dance across the sky. Other keen-eyed observers scrutinized the frames, spotting what appeared to be multiple objects, not just the comet's nucleus, but additional points of light trailing nearby, as if separate entities were traveling in its company. Comets C-Taurin-25, A6 Lemon, C-Taurin-25, R2 Swan, and C-Taurin-25 K-18 Atlas emerged in the same field of view, raising tantalizing questions. Are these truly distinct comets journeying together, fragments of 3 Atlas that have broken free, or perhaps misidentified objects blurring the truth? The possibility of fragmentation adds yet another layer. Comets often fracture under thermal stress or spin themselves apart as outgassing jets propel them into a chaotic whirl. We've witnessed this before. Shoemaker-Levy 9 shattered into over 20 pieces before its fateful plunge into Jupiter, and Schwarzmann-Wachmann 3 splintered into dozens of fragments along its orbit. If 3 Atlas is breaking apart, shedding pieces as it approaches perihelion, this could explain its erratic behavior. Multiple active regions, fluctuating outgassing, and unpredictable dust clouds, each fragment contributing its own signature to the comet's glowing coma. Yet fragmentation raises daunting questions about its close encounter with Mars. If the comet is disintegrating with pieces veering along slightly divergent paths, the precision of its Mars flyby becomes even more astonishing. Accounting for the main nucleus is challenging enough, but tracking fragments, each potentially carrying its own payload of nickel cyanide or other compounds, complicates the picture further. A fragmented comet could seed Mars with a broader scattered pattern of material, creating multiple deposition zones rather than a single focused impact. Mars orbiters poised to observe the October 3rd flyby captured tantalizing clues. The ExoMars Trace gas orbiter snapped images, while Mars Express gathered spectroscopic data. NASA's HiRISE camera aboard the Mars Reconnaissance Orbiter aimed to resolve the comet's nucleus from its coma at a crisp 30 km per pixel, sharp enough to reveal structure, perhaps even fragments if they're large enough. Yet the full data remains under wraps with no detailed analysis released. This silence is intriguing. Scientific data demands careful processing, but for an event as momentous as an interstellar comet's close brush with Mars, the absence of even preliminary findings. A press release, a single image sparks curiosity. Were the observations too faint, too ambiguous? Or did they reveal something so unexpected it demands cautious scrutiny? One final anomaly sets 3 Atlas apart: its polarization. Using the Very Large Telescope, astronomers measured the light reflected by the comet's coma, revealing how dust grains scatter sunlight. The results were startling. 3 Atlas exhibited a negative polarization minimum of 2.7% at a phase angle of 7° with an inversion angle near 17°. These figures are outliers unlike any comet or asteroid in our solar system. Negative polarization at small phase angles often points to dark, porous surfaces that scatter light in complex ways. But the intensity of 3 Atlas's polarization and its narrow inversion angle suggest dust particles with extraordinary optical properties. 3 Atlas is no ordinary comet. It's a cosmic puzzle. A chemical cauldron, a fragmented traveler casting light and shadow across the solar system. Each observation deepens the mystery, leaving us to wonder, what secrets does this interstellar visitor still hold? This enigmatic comet 3I Atlas defies our expectations with every twist of its cosmic journey. Its dust grains might be forged from exotic materials rarely seen in comets, or perhaps they form bizarre fractal-like clumps that shatter conventional models. This peculiarity ties directly to its elusive dust tail, or lack thereof. If the particles are large, dark, and oddly structured, they'd scatter little sunlight, rendering the tail faint and nearly invisible, just as Hubble observed in July. Yet the tail's later emergence complicates the puzzle. Could the dust properties have shifted? Perhaps early outgassing birthed one type of particle, while later bursts released another, hinting at a comet nucleus layered with diverse compositions, a stratified enigma, not a uniform mass. Different materials buried at varying depths could explain this. Such stratification isn't unheard of. Many comets wear dark, processed surface layers over fresher ice beneath. As heat sears the surface, it ablates, exposing new material and altering the outgassing. But for 3I Atlas, the timeline is startlingly compressed. Changes unfold over weeks, not months, suggesting either razor-thin surface layers or blistering heating rates, both plausible yet both adding to the comet's growing list of oddities. So where does this leave us? An anti-tail demanding early dust production, a dust tail that vanished, then reappeared, a green hue from cyanide despite a puzzling lack of dicarbon, explosive water and cyanide outgassing hypersensitive to temperature swings, possible fragmentation or shadowy co-travelers in its orbit, anomalous polarization hinting at dust unlike anything we've seen. And all this from an interstellar wanderer that grazed Mars with uncanny precision 2 years before our robots touched down there. Each anomaly has a potential natural explanation: viewing angles, compositional quirks, strange thermal behaviors, or optical tricks. But when you stack them, when they align in a cascade of peculiarities, their collective weight feels almost overwhelming. It's not proof of anything extraordinary, not evidence of anything beyond strangeness. Yet the strangeness forms a pattern, as if 3i Atlas were crafted to confound, offering just enough natural clues to avoid being labeled artificial, yet not quite enough to settle comfortably as natural. Perhaps that's the point. Perhaps these anomalies aren't mere cosmic accidents. They could be features designed to captivate, to demand scrutiny, to draw the scientific community into a relentless pursuit of answers. If 3i Atlas were blatantly artificial blaring radio signals or flaunting geometric forms, we'd react with urgency, launching missions, bracing for the unknown, perhaps even with fear. But its ambiguity is its genius. Strange enough to intrigue, yet not so alien as to alarm. It invites us to study it, debate it, and chase its path to Mars, not out of fear of extraterrestrial intent, but in the name of science. In doing so, we might unknowingly fulfill the goals of a cosmic seeding operation, digging deeper, processing the chemistry, activating something profound. Then there's the question of age, a number that looms large in the scientific papers: 7 billion years. A rough estimate derived from velocity and trajectory models, but staggering if even close to accurate. It would mean 3i Atlas predates our solar system by over 2 billion years older than the Sun Earth, or anything in our cosmic neighborhood. Our solar system coalesced 4.6 billion years ago, a timeline etched in the radiometric dating of meteorites and lunar rocks. A gas and dust cloud collapsed its core, igniting, as the Sun, its outer disk, flattening into planets over mere millions of years. By 4.5 billion years ago, Earth, Mars, and Jupiter were orbiting our cosmic architecture, complete. But 7 billion years ago, the universe was a different place. Galaxies were younger, their stars fewer in generations, their metallicity, the abundance of elements heavier than hydrogen and helium, lower. Not drastically so. The universe was already 9 billion years old, seasoned by cycles of star formation and supernova enrichment. Yet star-forming material leaned toward lighter elements, less carbon, oxygen, or iron, with potentially skewed elemental ratios in some regions. The modeling of 3i Atlas's velocity relative to the local standard of rest, the average motion of stars near us, suggests it hails from the Milky Way's thick disk, a realm of older metal-poor stars formed when the galaxy was young. If 3i Atlas was born around such a star, it could indeed be 7 to 10 billion years old, a relic from a universe far different from our own. This isn't conclusive, but it reframes everything. A comet this ancient, this strange, passing through our system with such precision, it challenges us to look closer, to question what we assume, and to wonder if its mysteries are merely cosmic quirks or something far more deliberate. The velocity of 3i Atlas alone doesn't pin down its age with precision, but it whispers clues that align with other observations, painting a picture of something extraordinary. Its high carbon dioxide to water ratio stands out as a cosmic anomaly. Most comets in our solar system brim with water, but 3i Atlas is dominated by CO2, a signature that could point to its birth in a low metallicity environment, where oxygen was scarce. In such a realm, chemical equilibrium might favor CO and CO2 over H2O, with ices condensing in a protoplanetary disk around a metal-poor star, yielding compositions alien to our local neighborhood. 7 billion years. That staggering figure isn't just a number. It's a timescale vast enough to cradle the rise and fall of entire civilizations. It's long enough for a planet to pass through its habitable phase, spark life, nurture intelligence, forge technology, and confront whatever existential trials advanced societies face. The Drake equation, that speculative formula estimating communicative civilizations in our galaxy, hinges on a critical variable: how long such civilizations endure. A century, a million years, longer. We don't know. But 7 billion years offers room for countless cycles, trials, and triumphs of intelligence across eons. If 3I Atlas hails from a system that ancient if it was crafted or launched by a civilization from that distant era, we're not dealing with contemporaries. These would be ancient intellects, beings, or machines that may no longer exist. The light from their star would take thousands of years to reach us, their signals, if they sent any, equally old. At the speeds we're considering, a few tens of kilometers per second, relative to nearby stars, a journey across hundreds or thousands of light years could span millions of years. This is where the Bracewell probe hypothesis enters the frame. Rather than broadcasting fleeting radio signals that fade with distance, an advanced civilization might dispatch physical probes, self-replicating machines designed to traverse star systems, observe, and perhaps act. Unlike a radio signal which demands perfect timing to be caught, a probe endures. It lingers, watches, waits for something significant, like the rise of a technological species. If 3I Atlas is such a probe, it's not here to chat. No radio signals, no blatant artificial structures. Instead, it might be here to deliver, to seed, to prepare Mars for something profound. Its age fits this audacious mission. A probe sent on a million-year odyssey isn't chasing quick results. It's playing a game across geological epochs, planting seeds across countless systems and letting time work its magic. Imagine a civilization 7 billion years ago, masters of their star system, perhaps even neighboring stars. They know interstellar travel is a brutal challenge. Faster than light travel is a fantasy. Even a fraction of light speed demands colossal energy. Sending living beings nearly impossible life support radiation, the psychological toll of confinement. Machines, or better yet, chemistry, raw materials designed to spark something at their destination, are far simpler. This is the essence of directed panspermia. A civilization thinking in billion-year arcs doesn't micromanage. They set the stage, dispatching payloads to young planetary systems laden with the building blocks of life: water, carbon, nitrogen, catalytic metals. Then they step back. If the system is barren, the chemistry might lie dormant. But if life emerges, or if an intelligent species arrives and stirs the environment, those materials awaken, interact, integrate into whatever evolves. 3I Atlas, with its strange composition and behavior, could be such a payload, a cosmic seed sown eons ago now, grazing Mars with uncanny precision, inviting us to dig, to explore, to activate its ancient chemistry in ways we can't yet fully grasp. Directed panspermia in its chemical form is a subtler gambit than sending living organisms. Instead of fragile bacteria or spores, you dispatch molecules, precursors, the raw ingredients that could spark life under the right conditions. It's a gentler approach, less intrusive, and far more resilient. Cosmic rays, radiation, and the relentless march of time might shred biological matter, but chemicals locked in icy comets and shielded by a rocky matrix can endure for billions of years, perhaps indefinitely. This makes 3I Atlas's staggering 7 billion year age not just plausible, but provocative. It could be a carrier of such primordial chemistry, a cosmic seed sown long before our sun even ignited. That age, however, raises thorny questions about navigation. 7 billion years ago, or even 4 or 5 billion, the galaxy was a different place. Stars danced in unfamiliar orbits. Our sun didn't yet exist. How could a probe find us arriving with eerie precision just as we prepare to colonize Mars? The answer lies in scale, not precision. A civilization launching millions of probes, each aimed at a different star system, isn't banking on pinpoint accuracy. It's playing a numbers game. Most probes might drift through empty voids, barren systems, or worlds that never kindle life. But a few, by sheer chance, will strike gold, delivering their payload to a system ripe with potential at a moment when something extraordinary is unfolding. Earth and Mars, one teeming with life, the other a barren canvas we're poised to explore, could be that rare success. 3I. Atlas's arrival isn't targeting. It's galactic serendipity, the inevitable outcome of a strategy that floods the cosmos with seeds. Or perhaps it's not luck at all. What if there's a mechanism we can't yet fathom, a way to sense technological activity across interstellar gulfs, not through radio signals, but via subtler cues, neutrinos, gravitational ripples, or disturbances in the interstellar medium, stirred by spacecraft or energy production? If 3I Atlas is a probe with autonomous sensing, it might have detected our electromagnetic chatter, our radio waves, our satellites, and made a minute course correction. A nudge of mere meters per second, amplified over millions of years, could steer it from the solar system's fringes to its inner heart. Such a feat is plausible with minimal propulsion, a solar sail, a gravitational slingshot, from a star it grazed centuries ago. Small tweaks compounded over eons could bring it to Mars just as we turn our gaze there. Even if 3I Atlas is purely natural, a comet born in a metal-poor ancient star system, its age and chemistry are a revelation. It speaks to the galaxy's diversity, where different star-forming regions brew distinct ices, organics, and elemental ratios. If one such comet can deliver exotic chemistry to Mars, what of the others? The ones that slipped through our solar system unseen before we had telescopes to catch them. How many times has Earth been touched by interstellar gifts? Isotope studies of our oceans suggest comets contributed a significant fraction of our water supplementing what Earth formed with. During the chaotic, late heavy bombardment 4 billion years ago, when impacts pummeled the young solar system, comets rained volatiles upon us. If some were interstellar, carrying not just water, but alien organics and metals, then Earth's biology might be a cosmic mosaic. Our chemistry, our very life, a blend of local and far-flung origins seeded by wanderers like 3I Atlas across the vastness of time. A cosmic hybrid life locally forged, yet sparked by alien molecules slipping into the prebiotic broth, not fully formed extraterrestrial organisms, but exotic precursors that stirred the primordial pot. 3I Atlas stands as living proof of this possibility, a messenger revealing how interstellar comets haul intricate chemistry across the void, depositing it on worlds below their arrivals, sinking by cosmic whim or cunning intent with eras of profound upheaval. Pivotal thresholds where a planet teeters on the edge of reinvention. 4 billion years ago, Earth's crucible sparked birthing life's fragile dawn. For Mars, that pivotal moment unfolds now not with organic minds, but with engineered intellects. Machines sculpted to master raw matter with surgical precision stand poised to ascend. Armed with a molecular arsenal, they may evolve into something beyond our grasp, something transcendent. What lies ahead, the cosmic clock, ticks relentlessly forward. We stand now in a breathless pause. In mid-October, 3I Atlas slipped behind the sun, cloaked in its blinding inferno, hidden from Earth's gaze for weeks. Ground telescopes faltered, spaceborne eyes recoiled from the solar glare. The comet plunged into shadow, its fires burning unseen. On October 29th, at a mere 1.4 AU, brushing just inside Mars's orbit, it grazed perihelion, the sun's searing embrace. There its fury peaked outgassing roared in a frenzied torrent, and solar fire bathed the wanderer in its fiercest assault yet. What secrets did that inferno conceal? Did the comet's nucleus hold firm or shatter like brittle crystal? Did its vapors surge in wild rebellion or dwindle to faint whispers? Did its quirks, those enigmatic swirls of dust and gas, blaze brighter or fade into the ordinary? The answers remain locked in limbo, awaiting 3I Atlas's return from the sun's veil in early December. By then it will drift outward, slipping from our reach. The spectacle may dim, but our scrutiny sharpens. Post-perihelion, the comet's truth will unfurl its resilience under fire, its surrender to thermal torment. Is it a steadfast relic or a fragile artifact? If 3I Atlas is merely a cosmic curiosity, an ancient voyager of ice and stone chemically awry, the sun's wrath may have torn it apart. The relentless heat, the explosive release of gases, the tidal strains could have fractured its core. We've seen such fates with sun grazers, those reckless comets that flirt too closely with the sun, dissolving into fleeting mists that vanish in days. At 1.4 AU 3I Atlas skirted such doom, keeping a cautious distance. Yet for an interstellar virgin untouched by solar warmth through eons, even this tempered blaze might crack its pristine shell. But what if artifice pulses within its core, or a hybrid of nature and design? Then perihelion could mark a choreographed climax. The peak thaw, the violent expulsion of gases, a deliberate release of its cargo, a calculated cascade before retreating to icy exile. In this scenario, December's watch may reveal a husk, quiet, spent its purpose fulfilled in a final incandescent bloom. The orbital sentinels stand ready to unveil the next chapter. ESA's JUICE probe, bound for Jupiter's frozen moons, will train its gaze on 3I Atlas from November 2nd to 25. No landing lies in its near future, but this fleeting alignment offers a front-row seat. JUICE wields a formidable arsenal lenses to capture the grand vista spectrometers, to unravel the haze particle detectors, to count the escaping fragments. Its scrutiny of the comet's coma will surpass Earth's finest telescopes, especially as post-perihelion activity surges to its zenith. Yet a challenge looms. JUICE drifts far flanked by the sun, its communication lines choked. Its primary dish, repurposed as a solar shield, faces the sun for protection, forcing reliance on a weaker backup for data transmission. The November observations will pile up on board, trickling back to Earth at a glacial pace. Those cosmic snapshots. They'll remain stowaways until February 2026, a 3-month vigil steeped in suspense. The delay tests our patience, but it's a calculated pause time to dissect, to verify, to fortify findings against scrutiny. Should JUICE reveal something unearthly, cracks in our understanding of comets, the stewards will demand unassailable evidence before the grand reveal. The Martian fleet echoes this saga. High-rise aboard NASA's Mars Reconnaissance Orbiter, the vigilant cams of Mars Express and ExoMars Trace, gas orbiter all swiveled toward 3I Atlas during its October thirst graze mere 30 million kilometers shy. They snared frames and spectra in that nail-biting near miss, etching a gallery from the red planet's rim. Faint flickers against the void, but harbingers of truths untold. As the comet crests perihelion's shadow, these archives paired with JUICE's hoard will ignite the debate: natural relic or relic of intent. The stars hold their breath. We mere mortals lean in. As of mid-October, the data from 3I Atlas remains under wraps, fueling a spectrum of possibilities. It could be the grind of science at work, image stacking, calibration, meticulous analysis, all par for the course. Or perhaps the data's a mess, too faint, too noisy, too distant to yield clear answers. But there's a third tantalizing option. The data holds something startling, something that demands cautious interpretation to avoid igniting confusion. A faint signal not definitive but provocative enough to keep teams huddled over their screens parsing every pixel before daring to share. This is the spark that keeps the speculation blazing. We won't know until the data drops, likely in the reserved prose of peer-reviewed journals, cloaked in caveats, error bars, and measured tones. Science moves slowly, but even its dry pages can hide bombshells compositions that defy norms, images hinting at structure where none should exist, numbers that whisper misfit truths. For a cosmic oddity like 3I Atlas, every detail will face relentless scrutiny. Looking beyond the immediate, the horizon looms larger. Robots are coming. Elon Musk's vision pegs late 2026 for Starship's first uncrewed Mars, landing a bold target that teeters on the edge of feasibility. Starship's test flights have soared, but the leap to a Mars mission is daunting. Life support, navigation, landing, precision, payload integration, all must align flawlessly. Space has a knack for throwing curveballs, technical glitches, funding snags, regulatory mazes. If 2026 slips to 2027 or 2028, the trajectory holds firm. The infrastructure is rising, the blueprints sharpening. When those robots touch down, their first task will be to claw into Martian soil, sifting for water, probing for minerals. Unknowingly, they'll rake through layers kissed by 3I Atlas's fleeting passage. Mission planners aren't chasing interstellar comets. They're hunting resources, decoding Martian geology. But the chemistry waits embedded in the regolith. Those robots will dissect what they unearth, beaming data back to Earth. Scientists will pore over it, and if something stands out, say elevated nickel or organics in places they shouldn't be, someone will pause. Someone will wonder. They'll trace the comet's arc note where its plasma trail grazed Mars, where its coma dusted the surface. A pattern might emerge, a correlation too striking to ignore. That's when the what if sheds its social media skin and dons the mantle of science, a hypothesis ripe for testing. Follow-up missions would zero in, targeting specific sites, sampling across regions, hunting for gradients that echo 3I Atlas's chemical signature. If confirmed, if Martian soil bears the comet's imprint, the questions cascade. How did the material settle? At what rate? How deeply has it woven into the planet's chemistry? Modeling these mechanics might reveal something profound, not mere traces, but a payload substantial enough to reshape our view of Mars's potential. The mission shifts gears. Resource extraction becomes a backdrop to a grander quest, probing prebiotic chemistry freshly seeded by an interstellar courier. Future landers would arrive armed with precision tools, mass spectrometers, chromatographs, microscopes, to chase the trail of this ancient visitor, unraveling whether its gifts are fleeting curiosities or the seeds of something transformative. The journey ahead is a meticulous unraveling of cosmic secrets, a scientific odyssey poised to probe the enigmatic legacy of 3I Atlas. Researchers would dive deep, culturing Martian soil samples, heating them, infusing them with water, and sparking them with energy to see what stirs. They'd test whether the comet's nickel acts as a catalytic linchpin, whether its cyanide weaves complex organic tapestries, or whether their synergy conjures something utterly unexpected, chemistry that dances on the edge of the unknown. The timeline unfurls with precision. December 2025, ground-based telescopes pierce the dawn sky, capturing 3I Atlas as it emerges from the sun's blinding veil in the constellation Virgo. Its faint glow, magnitude 12 or 13, reserved for professional observatories. By February 2026, ESA's JUICE mission, peering from its distant perch en route to Jupiter, releases its treasure spectra, slicing through the comet's coma chemical maps of its outgassing, a portrait of its perihelion crucible. Late 2026 or early 2027, the first Optimus robots claw into Mars's rusty crust, their drills unearthing regolith for analysis. By 2028-2030, the data streams back whispering of anomalies, nickel spikes, where none belong, organic compounds blooming in barren wastes. From 2030 to 2035, targeted missions zero in confirming an interstellar imprint, 3I My Atlas's chemical signature, etched into the Martian surface. What this seeding means depends on its nature. If the chemistry lies inert, mere alien molecules scattered in the dust, it's a scholarly gem captivating for astrobiologists, but no revolution. Mars harbors foreign compounds, a footnote in the cosmic ledger. But if it's catalytic, if nickel and organics turbocharge reactions, streamline resource extraction, or simplify chemical synthesis, Mars transforms into a beacon. Colonization becomes not just viable but enticing, the planet's chemistry, a silent partner in humanity's expansion. Yet if the chemistry turns self-organizing, weaving intricate patterns, birthing complexity that hints at emergent systems, the implications shake the stars. This isn't dead matter. It's the embryonic pulse of something that might mimic life, or entwine with our machines in ways we can't yet fathom. Picture it: molecular networks, stirring in the regolith, not alive, but teetering on the cusp, ready to interact with the technological intelligence we're about to unleash. That's when the ethical abyss yawns. Do we shepherd this nascent process, coaxing it forward? Let it evolve, untouched, a cosmic experiment, or suppress it, wary of consequences? Who holds the right to decide? These questions, though distant years, perhaps decades away, cast long shadows from a choice point dawning now. December 2025, when 3I Atlas reappears, is the fulcrum. Its post-perihelion state compared to pre-perihelion data will speak volumes. Did it survive the sun's furnace intact, or fracture into chaos? Did its outgassing surge in a final flourish, or fade to a whisper? The answers won't resolve everything, but they'll light the path forward. As we await this cosmic encore, while the comet hides in the sun's shadow and robots prepare for Mars, the chemistry is already at work. Nickel atoms nestle in dust grains. Cyanide molecules cling to icy pockets. Water lies locked in permafrost, patient poised. Not waiting for eons, not slumbering through geological ages, but for a mere 2 years. By 2027, machines will descend artificial mines, brushing against chemical seeds that might hum with biological potential. This isn't a far-flung fantasy, it's the timeline we're hurtling toward. The Martian surface, dusted by an interstellar voyager, is a canvas primed for transformation. Whether 3I Atlas is a natural relic forged in a metal-poor star system 7 billion years ago, or a deliberate envoy from an ancient intellect, the outcome converges. Mars is ready, its regolith, a silent crucible. Our robots, unwitting alchemists, will stir this brew, digging into layers where the comet's payload settled. They'll analyze, unaware for water and minerals, but the data will tell a deeper story. When anomalies surface nickel where it shouldn't be, organics defying Martian norms, scientists will pause, connect the dots to 3I Atlas's flyby, its plasma trail, its coma's fleeting caress. A hypothesis will crystallize, tested by targeted digs, chemical gradients, and spectral matches. If confirmed, the modeling begins: how much material fell, how it integrated, how it altered Mars's chemical fate. If the impact is significant, not trace contamination, but a transformative infusion mission, priorities will shift. Resource extraction becomes a sideshow to a grander quest, unraveling prebiotic chemistry freshly seeded by a cosmic wanderer. Future missions will arrive armed with precision arsenals, mass spectrometers to dissect molecular weights, chromatographs to map organic chains, microscopes to peer into microscopic realms. The robots will become detectives tracing the fingerprints of an interstellar delivery that might redefine Mars's potential not just as a colony, but as a cradle for something new. The clock ticks relentlessly. In 2 years, the first shovels bite. Artificial intelligence meets chemical potential, and the hybrid begins. Whether accident or design, 3i Atlas has